So let's look at arranging the formula for graphing. So we started off with this formula that we derived in the last video. If you need to, go back and have a look at this, the derivation of this formula. We ended up with a formula where r squared, let's try that again. Mosquito buzzing around my head. Where r is equal to, the range is equal to the initial velocity squared multiplied by the sine of 2 theta over g. Let me get this mosquito. And now what we might want to do with this is we might want to look at the relationship between r and one of the other variables in this formula, the variable of u or of theta or of g. So what we're going to ultimately try and do is if we can go and rearrange this formula into the equation y equals m, or the format y equals mx plus c, then we know that when we plot it on this graph here, it should come out as a straight line. So if we were going to go and look at compare the variable r versus u squared, then it should come out as a straight line. But we need to rearrange this formula here into the format y equals mx plus c. So let me get rid of this line here just for a second. Let's go back a step and let's write down y in this column. Then we've got mx plus c. Okay, so up here, let me draw some straight lines here. We'll put a straight line there, and we'll do a couple of those. Oops, there's that one. Go from here. No, draw another straight line. And one more. Okay, so we're going to try and rearrange our formula that we've got here into this equation, into this format. So we're going to say that r is equal to, so r will be the variable on the y-axis. R is equal to mx plus c. Well, this formula at the moment is not really arranged as mx plus c, but what about, I guess, if we did something like this? What about if we went and put, try that again. Let's put a bracket around that, and we're going to call that m. So we're going to say r is equal to the sine of 2 theta over g multiplied by u squared plus c. Now c is 0, so we're not going to have any c's in these examples. So what we're going to do here is we're going to plot r on the y-axis, u squared on the x-axis, and when we plot those points out, hopefully it'll come out as a straight line, where the gradient of that line will be the sine of 2 theta all over g. All right, what about if we don't want to just do what we just did then? Wow, fatal exception. All right, we got back from our fatal exception. Let's see if we can continue on and not die in the process. So what about if we don't want to do r versus u squared? What about if we want to do something else? What about if we're not looking at varying the initial velocity? What about if we're looking at varying the initial angle, I guess? So we want to go and plot r on the y-axis versus theta, or a component of theta. What could we do there? Well, I guess we could say, well, r is equal to, and we'll put it there because r is still on the y-axis. And we're going to try and arrange it now so that sine of 2 theta is separate. So let's go and do that. Let's go and say u squared on g multiplied by sine of 2 theta plus c. So this sine of 2 theta here now is going to go down here. Sine of 2 theta. So now we have something we're going to compare and see if we get a straight line relationship, a linear relationship between r and the sine of 2 theta. And if it works out as a straight line, then we're doing well. And we should know then that the gradient of that straight line is u squared over g. because that's what it says over here. U squared on G is the gradient. Sine of 2 theta is x. All right, let me get rid of some of these. Okay, and let's then go and have a look at another option, I guess, where we can say, well, what about if we put, now that the screen's a bit clear, let's see if we can put R against something else. What other variables have we got in here? I guess we've got G. So maybe we want to go and put R versus G. So what about if we then rearrange this formula and we take sort of G over the side here a little bit. We're going to say that U squared times the sine of 2 theta, and we'll make that 1 on G. X is 1 on G. So if I do 1 over G and I do R, then hopefully I get a straight line again, where the gradient in this case will be U squared times, the sine of 2 theta. Sine of 2 theta. Alternately, I could go and do it the other way around, where I could say R, I could make the gradient 1 on G, U squared sine of 2 theta. Again, I don't know that you'd want to necessarily go and do these, but you could. And if you want to plot R versus U squared sine of 2 theta, you know that the gradient should be 1 on G. You could go and work out what your gradient is. So actually plot your points of R versus U squared times the sine of 2 theta. You plot them out in your graph. And once you get a line of best fit, so you might have all these sort of dots all around the place. And once you do your line of best fit, you then use your formula for the gradient, which is the change in y over the change in x. You calculate what your gradient actually is, and you compare that gradient to 1 on G. So 1 on M should be the gradient, should be gravity. And you can compare and see what value you get for gravity. You could use this formula, this experiment, to actually calculate the value for gravity and work out the accuracy of your experiment.